Okay. So so network flows, we're just going to do a really, really brief coverage of network flows, because I realized I'm still not super rusted, but last time I was so tired that I drew what's this? Actually now I can give you all of them. Have I asked you any questions? I'm trying to think if I've put any questions on assignment 7 that I answered in a previous year. Because otherwise I can give you all the material for the 2 times I taught this course before. So last year I think I did the final like the midterms. But the first year I was super enthusiastic and I gave practice midterms before the midterms and practice final before the final, and so you can have all of that. But please don't freak out, because the practice final that year was horrible. I didn't realize it was quite as bad as it was. I mean, it was good, it was cool, but it was hard. Fortunately, the marks were nice and high going into the final, so it wasn't a complete slaughter. Actually, I think only almost nobody didn't get a C. I think a few, a handful, fewer than 6. I think maybe only 4 or something didn't actually get the course. This is the advantage of having huge numbers of people drop, is I don't have to fail people. Usually. I'm not guaranteeing that if you survive to the end of the course you pass. But it seems last year, it seems that way. Last year, of the 99 people who wrote the final, everybody got at least a C. Now, unfortunately, I'm invalidating that, because now people will hear this and think that if they can just hang on, then they're guaranteed to pass. No, it's like if you think you're not going to pass, then get out. You can. Well, I don't know. You don't get any money back if you quit now, do you? No, and you don't even get a W. I mean, there's the date, and you can withdraw, and you get the money back, and then you withdraw, and you don't get a bit of money back, and nothing shows up in your transcripts, and then you withdraw, you get no money, and you get a W, and then eventually, I think by this stage, it's too late. So good luck. Okay, so you might as well hang on and write the final. Yes, so I will, please, somebody, if I don't post it, somebody remind me, because it's a bit of a hectic week. Okay, so network flows. I have to start this. So there are 10 questions, and the last one is no. Okay, so hiding the chat. Did you start the what? Yes, I did, I think. I did. Okay. In case people think I'm talking to myself, there was a question. Did I start the small camera? Hi, recording land. Okay, so network flows. The problem with only showing you one class in these things is you're going to think the only thing you can do with network flows is problems about flows. Whereas it's actually sort of network flows are sort of beginning to get you into linear programming and duality and very cool stuff. And you can do a lot more with network flows than just flows. So there are problems on LeetCode. Unfortunately, I haven't got it. The example I'm going to show you is maximum bipartite matching, which you could probably do anyway. And without thinking of it as a flow problem. And it's still a graph problem. So there are other problems that we're not going to see where you can actually turn it into something that doesn't look like a flow problem, you can turn it into a flow problem. And then you can solve it by finding a maximum flow. So what is a flow? Well, that's sort of what it sounds like. You imagine you have like some network of pipes and stuff. Mighty reduction, yeah. Everything's reduction, because we don't actually like doing new things. We just like finding ways to make what we've done before. We like finding ways to solve new problems by using solutions we've already come up with, which is good. It's good software engineering. It's code reuse, and sometimes we can actually reuse the code. And also I want to get through this quickly because I realized I was so tired last time that I drew the example for Bellman-Ford, and then I didn't solve it. I just erased it. I drew like the infinities on it, and then I just wiped it out. And so you didn't actually see an example of Bellman-Ford. So if we have time at the end of this, we should. This shouldn't take too long. There's what is the maximum flow? Well, in the textbook, there's actually a nice Canadian example where you suppose that you have some factory that makes hockey pucks, and you have some warehouse. So you have your factory is in Vancouver, and your warehouse is in Winnipeg, right? And you want to ship pucks from your factory to your warehouse, because you don't want to make more pucks than you can ship. So this is the lucky puck example. At least it is in my textbook from the 90s. My copy before Stein joined CLR. So, but you don't own the trucking company. So you own the trucking company, and the trucking company says, okay, so we have this much space on trucks going in from these places to these places. So for example, every day you can ship like 13 tons, boxes, crates, pallets, whatever, 13 something or others, from Vancouver to Calgary. And there are trucks with space for 10 units, I erased something, going from Edmonton to Calgary, and trucks with space for 4 units going from Calgary to Edmonton. Okay? So, you look at this and you think, okay, well, I want to know how much I can get every day from Vancouver to Winnipeg. But that's not immediately obvious, even for this tiny, tiny little graph. It's kind of a mess. And you look at it and you think, how can I be absolutely sure that I've got that I found the best way to ship stuff? And also, you don't have to, like, not everything has to go in the same route. So you can think, if these were pipes with certain capacities, how much water could flow from Vancouver to Winnipeg? So, everybody clear on the problem? I'm going to take that as a yes. Okay. So, what you're going to do is let's in order to get this going, let's just start out by saying I'm going to send, can you read this? 12 of the 16. Can you read that? 12. Somebody's answering me. Yes, a little. Would it be better in, I don't know if you can see the difference if it's, the marker disappeared. So I have 2 reds, but I think they're equally good. Okay, so this is 12, maybe this one's a bit better. And then here I say, okay, I can only send 4, 4, 4. Right? So can you read this? Yes, okay, good. We're gonna not use that red marker then. We're gonna use this red marker. So, at the moment I'm sending 16 tons, crates, whatever, crates of pucks every day from Vancouver to Winnipeg. And that seems not bad because, I mean, obviously, okay, this actually is a deep theorem, but obviously I can't send more than 24 a day. Because, and this is actually called the max flow min cut theorem. If you can find a set of edges where if you cut those edges, you separate the source and the sink. The source is where stuff comes from, the sink is where it's going. And in more advanced formulations, you can have multiple sources and multiple sinks, and you can have multiple commodities coming, different commodities coming from the different sources. So you have pucks, and you have hockey sticks, you have something, but they're going on the same trucks, so blah, blah, blah. Okay, but so here we have one source and one sink. If you can find a cut, like this line, if I cut those two edges, I separate the source and the sink, then the capacity of the edges that are cut, that sum of the capacity, obviously the maximum flow can't be bigger than that. And in fact, there's a theorem that says the max flow is equal to the minimum cut. Okay? So there is a cut that has total capacity 24. So the max flow cannot be more than 24. Now, that's not guaranteed. It's not clear. Is that the minimum cut? I don't know. We haven't worked that out yet. But there is this theorem that says if I can find a cut, then I know that the max flow is not more, for any cut, the max flow is not more than the capacity of that cut. Therefore, I know that at the moment I'm getting 16 and I can't get more, I can't get more than 24. So I've got like 2/3, and on Dowell's grading scheme, 2/3 is a C and you pass, right? Okay, I'm gonna assume you pass. I pass. So this is maybe good enough not to get fired, but not quite good enough to get like promoted maybe. So we want to know what is the actual maximum flow. So, or equivalently, what is the minimum cut? So what we're going to do, we take this graph and we build another graph that looks something like this, but it's called the residual. Okay, and it's easier to draw than it is to explain. Yeah, I'm going to draw this in black as well. Yeah, I'm going to draw this over here. Okay. Oh, so the black number is the capacity, and the red number, the numerator, is what I'm actually sending. And this is still 10. I should have made this bigger. And I hope I'm doing this right. 7, and this is 8, this is 12, this is 4, and this is 9. Okay, so what is this weird graph? This is 7. Any chat messages? No, nobody's asking anything. Okay, so this graph is, okay, so this is the source and this is the sink. I'll just mark that. Usually the source is marked S and the sink is marked T. Okay, so what is this? Well, these edges are saying how much I can change the flow from that vertex, from between each pair of vertices, right? So here I'm sending, this is an unclear 12. I will rewrite that 12. I'm sending 12 units from Vancouver to Edmonton. And the capacity is 16, so I could increase that by 4, or I could decrease it by 12. So where is, oh, okay, so I don't have any of these complicated things. So, okay, here I could increase it, I could send 10 from Edmonton to Calgary, I could send 4 from Calgary to Edmonton. But I'm not actually using either of those. So the tricky thing here is, okay, for example, here I can increase by 9 going from Vancouver to Calgary, or I can decrease what I'm sending. So even though this edge only goes in one direction, there is the option to reduce the flow from Vancouver to Calgary. So that's why this edge is labeled 4. Because I can cut the flow by 4, I can reduce the flow by 4. Is this clear? Okay, so now what we want is something called an augmenting path. So that, it sounds fancy, but all it means is we want to look at this graph and say, is there a path from S to T? Because if there is, sorry, it's an augmenting path in this graph, I think. If there is a path from S to T in this graph, then we can take that path, take whatever numbers are along that path, and add it to these, and we're going to increase the flow. Well, we know how to find a path between S and T. So, for example, here, we could go here to here. So we're going to look for an augmenting path. So, I mean, ideally you want the augmenting path with the maximum minimum capacity, right? Because the amount of stuff you can send along the, well, it's like if you have a series of pipes, right? And you have some wide pipes and some narrow pipes. Well, the amount of water that you can push through is going to depend on the width of the narrowest pipe, right? It's like the weakest link. You can only put as much strain on something as the weakest link can take. I don't know if people remember that show. You are the weakest link. I never actually watched that, but people were saying that phrase. It was one of these reality shows, but I forget what it was called. It's like You're Fired, but it was like, I think it was British or something. Maybe it was Dragon's Den. I've never actually watched, so I don't know what these things are. I get these secondhand memes. I don't think anyone's actually told me I was the weakest link in any situation. There were several situations where they could have told me that, but I don't think anyone's actually said it. Okay, so So we're going to look for the path that has, we really want we want a path that maximizes the minimum capacity. And we could do that, but for the moment, let's just find a path, because we've studied paths to death. So for example, I'm going to say there's, we can go from S to, now just be thinking about how you would do this, right? Because you'd be like, oh yeah, like breadth first search, Dijkstra, whatever, is it reachable? Is it reachable as breadth first search? Okay. So you'd be like, oh, I could go here, and then I can go down, and then I can go over, and then I can't go this way, but I can go up, and then I can go down. And you could say, okay, on that path, from Vancouver to Edmonton to Calgary to Regina to Saskatoon to Winnipeg, which for distance terms, this is not super efficient. That's a long way. But the capacity, what's the minimum capacity? Well, here it's 4, here it's 10, here it's 10, here it's 7, here it's 8, so it's 4, okay? So the maximum capacity is, the minimum capacity on this path is 4. Now, I'm not guaranteeing that that's the largest minimum capacity. I haven't looked. But we're going to go in and say, okay, we're going to add 4 going from Vancouver to Edmonton. So this is now going to be, forget the 12 out of 16. Where can I put this? Okay, this is now going to be 16 out of 16. And then we're going to go from Edmonton to Calgary. So this is now going to be 4 out of 10. And then we're going to go from Calgary to Regina. So this is now going to be 8 out of 14. We're going to go from Regina to Saskatoon. So this is going to be 4 out of 7. And then we're going to go from Saskatoon to Winnipeg. So this is going to be 16 out of 20. So now, instead of having 16 out of 24, because we know that we can't get more than 24 because capacity of this cut, now we're getting 20 out of 24. So yay, 20 out of 24 is not bad, right? I mean, that's like 5/6. So that's 84%, that's an A, right? Ooh, there is a chat. Yes, okay. That was probably I don't want to raise my hand. Okay, that was probably an answer to a question I asked before. Okay, so now we said, oh, but is that good enough? Maybe we could get even more. So we check again. So now all we can do, is this the bad black marker or the good black marker? Because even it's good that the course is ending. I mean, I'm sure that people think it's good that the course is ending anyway. No, both my black markers are dying. Okay, so I think the blue marker is still okay. Okay. This marker is slightly better still. Okay, so now we can't increase the flow from Vancouver to Edmonton at all. So this is going to have 16 just going in this direction. We can increase this still by 9, and we can decrease it by 4. That hasn't changed. Now we can reduce this. We can we can increase the flow from Calgary to Edmonton by 8. And what does that mean? That means that we stop because net, everything is net, not hockey net, even though we're talking about pucks, but net transfer. So if we want to send 8 from Calgary to Edmonton, well, how do you send 8? Well, you send 4 from Calgary to Edmonton, and you stop sending 4 from Edmonton to Calgary. So the net is 8. And we can increase this by 6. So we haven't done anything here, so this is still 9. We can increase this by 6, and we can decrease it by 8. I hope this is right. So we can increase this by 3, and we can decrease it by 4. We can only decrease this by 4. We can increase this by 4. And we can decrease it by 16. So does that look right? And here we can only decrease this by 12. Does everybody see how to build the residual from this, the graph with the capacities and the flow and the current flows? A little different at first, but yes, okay. So you're looking at how much you can increase for each pair of vertices. Where there's if there's no edge, then you can't do anything. But if there's an edge, you're looking at how much you can increase the flow going from U to V, how much you can increase the flow going from V to U. And in cases where, so like I said, this you could increase the net flow from V to U. So here you can't actually send 8 things, but you can send net 8 things by increasing this flow and decreasing this flow. Okay, so you can construct this. So now we're going to see, is there any way to, is there an augmenting path? So is there a way to get from S to T? And it looks like there is, right? Because we can go from here to here, to here, to here, to here, right? So there's, now I just sort of picked this path out. I mean, you know how to find paths, because you've got a whole lesson on it. We never modified S's Saskatoon to Calgary. Right, so we never went from, so we can't reduce